The set of real numbers contains many common sets of numbers you will encounter in mathematics. Starting with the natural numbers, which sometimes are referred to as the counting numbers, it starts with 1, and then we increase it by 1 to get each next number within the set. So it includes 1, 2, 3, and then we continue in that fashion indefinitely, which we represent with this ... In these sets, the ... means continue in this fashion indefinitely. So 1, 2, 3, ... tells us to continue increasing by 1 to get to the next number as we go towards a positive infinity. A bold capital N is used to represent the set of natural numbers. The set of whole numbers is just the natural numbers with 0 included. A bold W is used to represent this set. Also, we can represent this set as our bold N, which is the natural numbers, union the set containing just 0. The set of integers contains all of the whole numbers, but also contains the negative natural numbers as well. So the integers contains the 0, 1, 2, 3, ... as well as -1, -2, -3, ... where we just continue in that fashion towards negative infinity. A bold capital letter Z is used to represent this set. The set of rational numbers contains all of the integers that we've defined before, as well as any fraction that contains an integer in the numerator and denominator, but the denominator cannot be equal to 0. A bold capital letter Q is used to represent this set. So the set of rational numbers is a set of all numbers a divided by b, where a and b are integers, and b cannot be equal to 0. Writing out a rational number as a decimal, they either have a terminating decimal, which ends after a finite number of digits. This includes numbers like 22 divided by 10, which is equal to 2.2, where the decimal ends, or say 333 divided by 100, which is equal to 3.33, where the decimal ends as well. Rational numbers also can have a repeating decimal, where there's just a sequence of digits that repeat indefinitely after the decimal point. These include 1 divided by 3, which is equal to 0.33333, ... where 3 repeats indefinitely. Or this can include 7 divided by 13, which is equal to 0.538461. And then that sequence of numbers repeats indefinitely over and over and over again. Whenever we find these repeating patterns, we usually put a bar over top of the sequence of numbers that are repeating. In short, rational numbers either have a terminating or repeating decimal. Moving on to irrational numbers, we get our first set that does not contain all of the previous defined sets in the video. Irrational numbers are any numbers that cannot be written as a rational number. Essentially, for an irrational number, it cannot be expressed as a ratio between two integers, a divided by b, where b cannot equal 0. The decimal definition here is the opposite of the decimal definition for rational numbers. Since rational numbers could terminate or have a repeating decimal, irrational numbers must contain an infinite number of digits with no repeating sequence of digits, essentially no pattern. Popular irrational numbers include pi, e, the square root of 2 or the square root of 3, as well as the negatives of these numbers. All of these numbers are characterized by decimal representations where there are an infinite number of digits with no repeating patterns. It is important to note that the set of rational numbers and irrational numbers are disjoint. They have no elements in common. All irrational and rational numbers combined together make up the set of real numbers, which we denote with a bold capital letter R. With the definition of the set of real numbers, we normally denote this set of irrational numbers as the reals take away the rational numbers, which is written in this form here. These are the most common sets used when dealing with real numbers. I'm Joe, and thanks for spending some time with me.